Continue with section 4.7. We're going to build a better can. So a better can. By this I mean a better can of pop in this case. Standard beverage container contains 12 ounces. If you allow a little bit of room up on top, we're going to round this off to a total volume of 22 cubic inches. So I want to design a better can to hold those 22 cubic inches of volume. But first of all, what do I mean by a better can? Well, I mean that a can that's a little bit more environmentally friendly, requires less material to make. Now, over the years, they've made a lot of engineering improvements. It used to take 35 pounds of aluminum to make 1,000 cans, and it's now down to about 28 pounds. So that's pretty good because making aluminum is really, really energy intense. It takes a lot of electricity. But we want to do even better. So how are we going to do better? We're going to try and design a can that has minimal surface area. So let's see if we can't do that. Okay. Let's first of all come up with an expression that talks about the surface area of this. So here's our picture. There's not much we can do. We've got a radius and we've got a height. All right. Well, the surface area. There's two kind of main parts to the surface area. What are the main parts? What are the things you're going to calculate when you're finding the area of this surface? All right, so the lids here, the area of the base and the top. So area of top and bottom. What else should we account for when we're calculating the surface area of this can? Area of the sides, right? All right, so the area of the sides. Well, this should probably be singular, side. This is really just one, but in any case, let's start with the easier of these two. What's the area of the top and bottom? Close. 2 pi r squared. So the area of just one of these is pi r squared, right? The area of a circle. But you've got a top and a bottom, so 2 pi r squared. Now, as far as the area of the sides is concerned, well, that's a little bit trickier. So let me show you how we're going to deal with that. So imagine that you have just the sides here. And what I'm going to do is I'm going to slit down that side and then unroll it. Now what shape do I have? What area? Just a rectangle. So what's the area of a rectangle then? Base times height. So the height is h, the base is 2r. So it's going to be plus 2r times h. Okay, looking better. Call that S. But it's still not exactly where it needs to be. What else do I need to improve on this with? Yeah, we got an extra variable. Yes, sir. Oh, you know what? Thank you. Yeah, I wasn't thinking completely. Yeah, because one of these sides comes from the dimension of the circumference of this, right? Because when you unfurl this, then this side is going to be the length of 2 pi r. So I forgot the pi there. So 2 pi r h. Beautiful. Let's keep going. We need to come up with something to get rid of the h. Let's look back at the problem. Is there some information there that we haven't used yet? Volume. 22 cubic inches. What's the volume of a can? Or volume of a cylinder? It's going to be the area of the base times the height. So 2 pi, excuse me, not 2 pi, pi r squared times h. Pi r squared times h. All right. It's looking better. So pi r squared times h. How does that help me out? Or does it? Yeah, you can solve for h. So h equals 22 divided by pi r squared. And we can plug that into our formula over here. S equals 2 pi r squared plus 22 plus 2 pi r times 22 over pi r squared. Let's call this S of r now. This is 2 pi r squared. Pi will cancel out from both of these. What else will cancel? One of the r's. So that'll take out one of those. And you're left with 44 over r. Yay. So finally, we've got a nice formula. Picture, function, then what? There's an important step that we're skipping. Interval. So picture, function, interval analysis. So let's work on that. It's actually an F. What's our interval going to be? There is a little bit of a restriction. Not a big one, but there is a little bit of a restriction. Yeah, it can't be negative. You can't have a negative radius. Other than that, there's no restriction that I see. Now, there's going to be practical limits, right? I mean, you don't want an extremely wide can that's really, really short. I mean, it's possible to build one, but I'm hoping that the shape of our maximum is a little bit better than that. Yeah, it'd be like you're drinking out of a pancake, all right? It'd be, yeah. Well, it's going to be a cylinder shape. So, okay. Let's see, the analysis. S of r is 2 pi r squared plus 44. Let's write that as r to the negative first. It's going to be a little bit easier to differentiate. Differentiating is our only trick here, right? When you only have a hammer, everything looks like a nail. So let's find the derivative. You're supposed to laugh at that. Make me look good on these videos, right? Ah, thank you. Minus 44 r to the negative 2. We want to find the critical points. Remember, the critical points are where this could equal 0 or it's undefined. Where is it undefined? At r equals 0. But you know what? R equals 0 is not a point that we're worried about. It's not in our domain of interest. Actually, it's not in the domain of the function at all. So we're not worried about r equals 0. We are worried where s prime equals 0. So it's going to be 4 pi r equals 44. Let me put that in the denominator. R squared. Okay, so let's solve for r. Let's see. I'll multiply both sides by r cubed, or by r squared. Clear out the denominator there. So times r squared, 4 pi r cubed equals 44. I'm going to divide both sides by 4. Well, I'll divide it by 4 first. Pi r cubed equals 11. R cubed equals 11 over pi. So r equals the cube root of 11 over pi. Whew. Now what do we hope this point is going to achieve? What's it supposed to be? A max or a min? A max. Now it's up to you here, what you find most convenient. You can apply the first derivative test or you can apply the second derivative test. Neither one of them is that bad, but for me, I think the second derivative test is pretty fast. What would the second derivative be of this function? Good. 4 pi plus 88 r to the negative third. Let me just write that as over r cubed. If I put in this point, cube root of 11 over pi, what's the sign of the second derivative going to be? That's positive, 88 is positive, r cubed is going to be positive. This has to be greater than 0. If it's greater than 0, what kind of a point do I have by the second derivative test? Go ahead. A minimum, yeah, because the shape would be concave up. So if it's a concave up shape, then it has to be a minimum point. So there's your shape, concave up. So this is a minimum. The only thing we have left to do is figure out what the height is. What's the other dimension? Keep in mind that twice this is going to be the diameter of the can, right? So the diameter is going to be twice the radius. But we'll worry about that in a second. Let's first of all calculate what this is, and then we'll plug it back into our expression for h and see what we get there. So the cube root button is underneath the math menu. Fourth option down gives you the cube root. We want 11 divided by pi. The convenient thing to do for you is to store this. Store that in x, because plugging this in is kind of a pain. In fact, it's when I first did this problem and plugged it in and got a numerical solution, I found out something interesting about our can. This is what our expression is for h. It's 22 over pi r squared. So h equals 22 over pi r squared. I've already stored the value of r in here in my calculator. So let's actually calculate h then. So I want 22 divided by parentheses pi times x squared. And there's something interesting about this can. Look at the radius compared to the height. What do you notice? Double. If you double the radius, what distance do you get when you double the radius of a circle? Diameter. So basically, our new can has a diameter that's going to match the height. It's going to look square. When you look at it from straight on, it's going to look square. In fact, years ago, I had a neighbor who was a World War II veteran with the coolest wood shop in his garage. And he actually built me this can. So there it is. And he promised me that it was accurate to within 1/10,000th of an inch. I don't know. I think he's off. Whatever. All right. But here it is. Here's your can. Now, the question is, why don't people make cans in that shape then? I mean, that minimizes the amount of material that you would need. Why don't they do it? That's the main reason. Yeah, number one, you'd have to do a lot of retooling. All the machines that fill bottles and sell you your cans of pop would have to be re-engineered. That would cost millions. But most importantly, like Charlie said here, is that it doesn't feel comfortable. The consumer, you guys have a big say in this. And if you were trying to hold a can like that, it wouldn't feel very comfortable. You will see that shape in the supermarket, though. If you look at cans of like Fresh Like corn or condensed milk, they'll have a square profile. And what they're doing is they're minimizing the amount of surface material for constrained volume.
That's why they cost a lot.
No, I guess what what costs a lot is what's inside, not the can. I would think.
Like this can of Pepsi costs you the regular one is 109. Then you want to minimize the can, that's gonna be $2.
You know, the price of pop doesn't defies logic. I mean, you go to this grocery store, the 2 liters quite often sell for less than a 20 ouncer. Because 20 ounces are popular, they can charge what they want. It's price and supply and demand.
How many ounces is that? Like fluid
That would hold a little bit over 12 fluid ounces. So 12 fluid ounces converts to a little under 20 cubic inches. The extra space there is because you don't have liquid all the way to the top. You have a little space up top. All right. Any other comments on this one? This is actually very similar to problem number 28, and 27 is kind of similar. In problem 28, really what they're doing is they're asking you to play around experimentally with some values here to try and graphically estimate, what's the best radius, etc. So similar to problem 28, but not exactly 28. Yeah, same idea. Anything else on that one? Okay. Let's do one last one here. Problem 36A. So we've got 20 feet of wires to be used to form 2 figures. An equilateral triangle and a square. So we want to figure out how much wire should be used for each figure so that the enclosed area is a maximum. So we want to form an equilateral triangle and a square. On a problem like this, I might give you a little bit of a hint in terms of an equilateral triangle. In terms of its area, there's a nice neat formula that you can prove in a lot of ways, one of which would be trigonometry. Problem 36A. So we've got 20 feet of wire. Thank you. So we've got 20 feet of wire. And we're going to make a little cut in here someplace, so that we have a length of x, and the rest of it would be 20 minus x. We're going to bend those wires into 2 shapes. One into an equilateral triangle, and the other one into a square. So, okay. What's an equilateral triangle? Yeah. All 3 sides. All 3 sides have to be the same in an equilateral triangle. And then, of course, we also have a square. So let's draw a square with the remaining. So we're going to cut that wire into 2 shapes. We're going to find something that maximizes the area of these shapes. Now, just a little reminder here for ourselves. Some area formulas. Area of an equilateral triangle is square root of 3 over 4 times s squared. That's just for equilateral triangles. And it's putting the area in terms of the length of the sides. So that's kind of cool. What about the area of a square? S squared. Yeah. Now we're using, these are actually different s's. So let's figure out what they're going to be for this particular problem. let's use this to make our triangle. So if we do that, if we use the length of x for making this triangle, what's the length of each side? So in this case, it'd be x over 3. So the total area of figures is going to be square root of 3 over 4 times x over 3 squared plus something else squared. Now don't make Charlie do all the work here. Not quite. Because that 20 minus x has to get divided up into the entire length, right? It's not just 20 minus x this way. The whole thing is 20 minus x. 20 minus x over 4. Question? So let's call that a of x. This is a polynomial, in fact, it's a quadratic polynomial. So, okay, we got our picture, function, interval. Definitely there's restrictions on this. Now, as far as a polynomial is concerned, there's no restrictions. But as far as this is concerned, there is a restriction on x, right? Well, it's more than just positive and negative numbers. Yeah, 0 to 20, right? I mean, x is how much you're cutting off of this. Here's 0, here's 20. You can cut off anywhere between 0 and x. So it has to be in that interval someplace. 0 to 20. Now let's work on the analysis. I might want to clean this up a little bit. Good question, no. Because if you didn't cut off at least a little bit, you wouldn't have anything to make one or the other figure. You'd be making one figure or the other. I mean, I guess, I don't know. It's a good question. Maybe we should investigate the endpoints. Maybe it's best to just put it all in terms of the square, or maybe it's best just to put it all in terms of the triangle. So that's a good point. And this one, let's just do we'll check the endpoints as well. See if one is better than the others. Let me clean this up a little bit. This is going to be square root of 3 over 36 x squared plus, if I square this as 16, I'll take out the 1/16. What else am I going to have? Should I square this out as well? No, I'm not going to. 20 minus x squared. That's still a of x. Picture, function, interval, analysis. As far as the analysis is concerned, I need the derivative of this. So a prime of x. The 2 comes out here. Well, I'll write it down. 2 square roots of 3 over 36x plus 2 over 16. 20 minus x to the first power. I'm not quite done there, am I? Times negative 1. Good. You got to use a chain rule here. Derivative of the outside times derivative of the inside. Square root of 3 over 18 minus 1 over 8. There's an x here still. Minus 1 over 8 times 20 minus x. I want to know where that's equal to 0. Okay, so let's set that equal to 0 and solve. That's going to look ugly. Distribute the negative 1/8. Square root of 3 over 18x minus 20 over 8 is going to be 2.5. So we'll call it 5 halves. Minus 5 halves plus 1/8 x. I'm going to move the 5/2 to the right-hand side. Square root of 3 over 18 plus 1/8 x equals 5/2. Boy, isn't this a lovely number? 5/2 divided by square root of 13, square root of 3. Sorry about that. Square root of 3 over 18 plus 1/8. Eesh. Not exactly a friendly number, but that's one of our critical numbers. Okay, so we're going to have to check the function at those points. I'd suggest you just make a little table and check them numerically. In the interest of time, I'm going to speed things up here for us. Here's our value of x. Here's our value of a of x. Unlike most of our problems here, we are going to test the endpoint. There's nothing necessarily wrong with devoting all the material to the square or all the material to the triangle. Just have to see how it plays out. I think we kind of figure out one of them in our head. If we put in a 0 here, that would be 0. 20 over 4 is 5. 5 squared is 25. So at x equals 0, meaning all the material goes to the square, you get an area of 25. At our critical point, so I'm not going to copy it down, critical point, we get 10.875. And at the other extreme, what would this mean? If we put in an x equal 20, it means that we're throwing all the material into the triangle. Then you get about 19.245. If you're looking to maximize this, do you want to use the critical point? No. Actually, the critical point looks more like a minimum than a maximum. We'd have to investigate that. But the maximum is when you put all the material into the square. So, put all the material into the square. So if you look back at where we started, we got material put into a triangle or a square, and the best thing we can do in terms of maximizing the area is just to put it all in terms of the square. Okay, that's enough. Let me give you some homework. Yeah, no problem. I got your back here. 1 through 29. Homework 1 through 29. So it's like 15 problems. See ya.